Today's goal of this lecture. In my previous video I had seen what is the self-adjoint operators and properties of self-adjoint operator. Also in my previous video I had seen what is the eigenvalue of self-adjoint operator. Today's goal of this lecture, today I will see diagonalizability of self-adjoint operator. Then I will see what is the normal operators. This is today's goal of this lecture. Actually today's goal, today I will see diagonalizability of self-adjoint operator. Actually self-adjoint operator always be diagonalizable. We all of us know eigenvalue of self-adjoint operator always real. In my previous video I had seen. Today's goal of this lecture, today I will see self-adjoint operator always be diagonalizable. Then I will see normal operator. But at first I will highly recommend you please see today's video with pay attention, because today's video actually very conceptual. At first, just as a review, today I will see some example of self-adjoint operator and one example which is not self-adjoint. Actually, in my previous video I had seen definition of self-adjoint operator. If T be a mapping from operator from vector space to vector space and its adjoint who is defined as T star, who is defined from vector space to vector space, this is self-adjoint if T star equal to T. If T star equal to T, then T is self-adjoint. And in matrix notation, a n cross n matrix is self-adjoint, or in complex this is Hermitian matrix, and in real this is actually the symmetric matrix. When field is real, if A star equal to A, that means T is self-adjoint if T is equal to T star, and by inner product notation this is actually inner product TV with W is equal to inner product V with TW, and this is true for all V belongs to vector space and for all W belongs to W. I will see one operator which has no adjoint. The example, consider V and W equal to space of all polynomial on 0 1 with inner product f with g equal to integration 0 to 1 fx gx bar dx. Consider V equal to W equal to space of all polynomial, and here the operator is defined as differentiation operator. I will say T has no adjoint. Consider gt equal to 1, let gt equal to 1 and T star g equal to S. Then inner product TF with g, this is equal to integration 0 to 1. Here TF is differentiable operator, so this is equal to f dash x, and the value of g consider this is as, consider gx equal to 1, then f dash x and value of gx equal to 1 dx, and this value by the property of integration, this is actually fx integration from 0 to 1, this value is f of 1 minus f of 0. Actually To find the adjoint, we have to prove inner product Tf comma G is equal to F comma T star G, and here this value is equal to, I have got f of 1 minus f of 0, and this is equal to, since I have considered Tx equal to 1 and T star G equal to Hx. So this value is equal to integration 0 to 1 fx times Hx bar by the defined inner product. Because inner product f with g is defined as integration 0 to 1 fx gx bar dx here. And consider fx equal to x square times x minus 1 whole square times hx. Now put the value, this is integration 0 to 1 x square times x minus 1 whole square, hx times hx bar dx. And here f of 1 minus f of 0. And put the value of f of 1 here, this value is equal to 0 minus, and f of 0 also 0, so this value equal to 0. So this part is equal to integration 0 to 1 x square times x minus 1 whole square absolute value of hx whole square dx. And notice right hand side of integration is always positive, so this is greater than 0, and left hand side is equal to 0. So since left hand side and right hand side both not equal, so this type of inner product does not exist, so there exists no adjoint. This operator T has no adjoint. I hope my all viewers have understood clearly. Okay. Next, I will say what is the normal operators. Then I will say the diagonalizability of self-adjoint operator. Normal operator, consider S and T, who is mapping from vector space to vector space. In general, ST not equal to TS. If we consider this matrix 1, 2, 3, 4 with 1, 0, 0, 2, this is always not equal to 1, 0, 0, 2, 1, 2, 3, 4. So, S and T are commute when ST equal to TS. Identity operator, only one operator who is commute all operator, and normal operator is who is mapping from vector space to vector space is said to be normal if T star T equal to T T star. That means T commutes its adjoint. Then we can tell T is normal operator. I hope my all viewers have understood what is the normal operator. A self-adjoint operator always be normal. Why? Because self-adjoint means T star equal to T. If we multiply T on both sides, then T star equal to T square. And T square means T star T. So, that implies T star equal to T star T. So, here T commutes its adjoint. Okay. So self-adjoint operator that imply T is normal. So self-adjoint operator always be normal. But normal, this does not always imply this is self-adjoint. Few minutes later I will see this. Next, if T1 and T2 are self-adjoint operator, then T1, T2 are self-adjoint. If and only if T1, T2 equal to T2, T1. For this, given T1 and T2 are self-adjoint. That imply, since given T1 and T2 are self-adjoint, that imply T1 star equal to T1 and T2 star equal to T2. Then we have to prove T1, T2 are self-adjoint and let T1, T2 are self-adjoint. If T1, T2 are self-adjoint, then obviously T1, T2 star equal to T1, T2. And by the property of adjoint, this is equal to T2 star, T1 star equal to T1, T2. And since T1 star equal to T1 and T2 star equal to T2, that means this is equal to T1, T2. Therefore, T2, T1. Therefore, if T1, T2 are self-adjoint, then T2, T1 equal to T2, T1 equal to T1, T2. I hope my all viewers have understood. Conversely, let T1, T2 equal to T2, T1. Now, apply adjoint in both sides. T1, T2 adjoint, this is equal to T2 adjoint, T1 adjoint. And T2 adjoint means obviously T2 and T1 adjoint mean T1. That means T1, T2 adjoint equal to T2, T1. That implies T1, T2 are self-adjoint. I hope my all viewers have understood. This is okay? Oh well. Now I will see diagonalizability of self-adjoint operator. Actually, self-adjoint operator always diagonalizable. We all of us know in any finite dimensional inner product space, any basis x1, x2 up to xn transform to orthogonal basis, and we can solve this by Gram-Schmidt method. x1, x2, xn transform v1, v2 up to vn, where v1 equal to x1, v2 equal to x2 minus inner product x2 with v1 divided by inner product v1, v1 with v1, and v3 equal to x3 minus inner product x3 with v1 divided by v1 inner product v1 with v1 times v1 minus inner product x3 with v2 divided by inner product v2 with v2 times v2, so on. That means in finite dimensional inner product space, any basis transform to orthogonal basis. By Gram-Schmidt method, we can tell this. We all of us know the source lemma. Given any matrix A of size n, there exists always unitary matrix U such that U star AU is upper triangular matrix. If we consider T equal to upper triangular matrix, then always T equal to U star AU. That means this is actually unitary similar to upper triangular matrix. By Schur's lemma we can tell, given any matrix of size n, there exists always unitary matrix U such that U star AU is an upper triangular matrix, and if we consider T, then T equal to U star AU. And when the operator is self-adjoint, consider T be a mapping from Cn to Cn such that T star equal to T, then by Schur's lemma, always there exists upper triangular matrix. Always there exists upper triangular matrix with respect to orthogonal basis U1 up to UN. That means with respect to orthogonal basis, always we can construct one upper triangular matrix by Schur's lemma. Consider this is A11, A1, A22 up to this is the diagonal element. Since this is similar to upper triangular matrix, this is similar to this type, but since the operator is self-adjoint, so obviously this part would be 0. That means A is similar to only the diagonal matrix A22 up to AN, and other part is 0, 0. That means when the operator is self-adjoint operator, then this is similar to actually the diagonal matrix. I hope my all viewers have understood. Next, suppose V be finite dimensional real inner product space and let T be linear operator on the vector space V, and beta be orthonormal basis for the vector space V such that matrix representation with this basis is diagonal matrix. If matrix representation with orthonormal basis always be a diagonal matrix, then T is self-adjoint operator. That means this is another way to find a operator is self-adjoint or not. If the matrix representation with respect to orthonormal basis is diagonal matrix, then we can tell this is the operator is self-adjoint. Also, we all of us know definition of diagonalizability. If V be a finite dimensional inner product space over F and T be linear operator on F, then T is diagonalizable if there exists one beta for the vector space V such that the linear transformation with respect to this beta is diagonal matrix, then we can tell the operator T is diagonalizable. That means if there exists beta such that linear transformation with respect to this beta is diagonal matrix, then the operator T is diagonalizable. Since in self-adjoint operator always there exists a orthonormal basis, and with respect to this orthonormal basis the operator matrix representation is diagonal matrix, so obviously this operator is diagonalizable. So self-adjoint operator always diagonalizable. Also, we all of us know the fundamental theorem of algebra. Let Px be polynomial with complex coefficient, then by fundamental theorem of algebra we can tell the polynomial splits over the complex number. Then my next question, how the fundamental theorem of algebra impact on self-adjoint operator? Since actually characteristic polynomial of self-adjoint operator always be split. Either it is real inner product space or it is complex inner product space. So we all of us know when a polynomial be splits, then always the matrix is diagonalizable. So the proof is pick an orthonormal basis beta of the vector space V, and with respect to these orthonormal basis construct one matrix A. The matrix A always be complex entries, and let f lambda be characteristic polynomial of A by fundamental theorem of algebra. The f lambda equal to lambda minus lambda 1, lambda minus lambda 2 up to lambda minus lambda n, where obviously this lambda I be the eigenvalue of the matrix A. And since the matrix A is self-adjoint, obviously this lambda I are real for all r. And since f lambda is split, then we can tell the operator T is diagonalizable. T is diagonalizable. Either it is complex self-adjoint operator as well as real adjoint operator. So by fundamental theorem of algebra we can tell the operator T always be diagonalizable. That means I have got the operator self-adjoint operator always be diagonalizable. And in my previous video I had seen the eigenvalue of self-adjoint operator are real. Now let's see some example from R2 to R2 such that T of xy equal to yx. Let beta be the standard basis. And with respect to the standard basis, the matrix representation is 0, 1, 1, 0. And obviously adjoint of this matrix is 0, 1, 1, 0. So T star xy equal to actually yx, which is equal to T of xy. So T star xy equal to T of xy. So that implies T is self-adjoint. Second, similar type example T from R2 to R2 such that T of x comma y equal to here y comma minus x. And with respect to the standard basis, the matrix representation is 0, minus 1, 0, 1, 0. Obviously, T star with respect to the standard basis is 0, minus 1, 1, 0. 0 plus 1 minus 1, 0. That means T star x comma y equal to minus y comma x. So T is not self-adjoint, but obviously T is normal. I hope my all viewers have understood all properties of self-adjoint operator. Okay? Oh well. That means, but if you check, you will see Here T star equal to T star T. That means T is normal, but T is not self-adjoint. Therefore, this is the example I have seen it. I have told you few minutes ago, self-adjoint operator always be normal. But normal, does not always imply this is self-adjoint. This is the example. This operator is normal but not self-adjoint. I hope my all viewers have understood this is okay. Well, today I will stop here. In my next video, I will discuss normal operator and properties of normal operator briefly. But at first I will highly recommend you please see today's video with pay attention. Because today's concept actually very important for higher study. Okay? See you soon. Stay safe and stay positive always. And don't forget to subscribe my channel for more videos. Thank you so much.